This is joint work with Constantin Enea at the University of Paris 7. What this work is about, is the microphone volume a bit high? Is the microphone volume too high? No, it's okay? Okay. So this work is about verification of concurrent collections. Concurrent collections are crucial for performance in many multi-threaded applications, yet they're error-prone and notoriously hard to verify. Now, in this talk, when I talk about verification, I'll really be speaking about event-based runtime verification. And what that means is we're not trying to reason about the source code or the binary code or the implementation of a given data structure, but we're going to be reasoning about the call and return actions and its traces that such code enables. So we're only going to be reasoning about the call and return actions of operations. So the basic result of our paper is we identify a certain class of collection abstract data types which admit tractable verification problems, despite the fact that for arbitrary abstract data types, the checking correctness of them is intractable. Now, the approach that we're going to take is based on a symbolic encoding of the verification problem. And essentially, and I'll get into what this means as we go, but essentially it's going to replace an enumeration of linearizations based on some kind of search through the space of all possible linearizations with a more deductive style inference technique. The impact of this work is the first sound, complete, and tractable verification, runtime verification algorithms for concurrent objects. So just to breeze over real quickly what I'm talking about here, concurrent objects are specialized high-performance shared resources used in multi-threaded programs. So multiple threads can, for instance, access this queue data structure, concurrently enqueuing elements, dequeuing elements, both at the same time, by an arbitrary number of shared threads. So these are designed to work with unbounded numbers of threads and so on. These are provided by the standard libraries of many and also non-standard libraries of many popular programming languages. The Java Development Kit Standard Edition, for instance, includes dozens of objects, including queues, maps, sets, all of the things you normally think of as collections, as well as locks, atomic integers, and other things like this too. Now, these data structures are interesting because unlike arbitrary transactions of concurrent operations, specializing the abstract data type admits efficient implementations. So just to contrast this with a reference implementation that may do blocking mutual exclusion-based concurrency controls and synchronization, for instance, if we just looked at the execution of two threads above where a first thread does an enqueue operation. So a mutual exclusion-based implementation of this, when the second thread does his first enqueue operation, he has to wait until the first thread's enqueue operation completes. So this is a pretty big synchronization bottleneck that is avoided by good implementations of data structures. Instead, the bottom execution would be an execution of a typical non-blocking data structure, which uses atomic instructions like compare and swap or fetch and increment. These are atomic specialized processor instructions. And as you can see in the way I've drawn it here, it really gets rid of a lot of the synchronization bottleneck in the sense that each operation can execute concurrently only with a small synchronization overhead for executing an individual atomic instruction. Now, there is still some overhead because the atomic instructions have to synchronize the caches between different threads if they're running on different cores and so on. But the overhead is typically much lower and the performance is much higher than lock-based implementations. Now, this is a caveat. It depends on which data structure you're talking about and which implementations, but this is generally believed to be true. But using these low-level synchronization primitives and trying to squeeze out as much performance as possible is error-prone. It's not hard to find bugs in many of these implementations. So correctness is really an issue, and that's why we're talking about verification. The correctness criteria for these concurrent data structures is commonly what's known as observational refinement of a given abstract data type. So in this case, if I have an implementation of a queue, maybe Java's concurrent linked queue, for instance, I will have an abstract data type of a queue behind it with enqueue and dequeue operations. So the question of whether this particular execution is accepted or not, admitted by that queue, we just have to reason about the queue abstract data type. The queue abstract data type is non-deterministic. When there are concurrent operations, it can choose which one it decides somehow happens first. So if we just try to explain this execution based on the queue abstract data type, we have that the queue may, even though the enqueue of 2 on the second thread is called after the enqueue of 1, the queue abstract data type can say, well, the 2 was put in there first, then the 1 was put in there. The queue's type is represented just by a sequence of elements that have been inserted. And so this abstract data type explains this execution in which 2 is dequeued before 1, even though 2 was enqueued, well, the call of enqueue of 2 happened after the call of enqueue of 1. These operations were concurrent. So there's a lot of non-determinism here and a lot of flexibility into what are the possible return values of any given DQ operation. But there are some strong guarantees too. For instance, that each added element is removed at most once. So if I put in the element 1 and then put in the element 2, I cannot DQ 1 twice, for instance. It also ensures things like if the add operations of any two elements were ordered, then the remove or DQ operations also have to be ordered. So mechanizing observational refinement is done by a related criterion called linearizability, which was introduced by Herlihy and Wing in 1990. The idea of linearizability is that the effect of each operation has to occur or appear to occur at some point in time instantaneously. So again, just looking at how we'd explain this particular execution of the queue, we have to choose a linearization point per operation, and the ordering of those linearization points will admit what's called a linearization, and now we have to decide, is this linearization admitted or not by the QADT? And the question of linearizability is then, does there exist a linearization of all possible linearizations such that the QADT admits it? So this criteria was known to imply observational refinement for some time. More recently, it's been shown that it's actually complete, so observational refinement actually implies linearizability as well. However, checking linearizability is hard, and it's not too hard to see why. So if we just take this pretty similar execution history again, in general, there's an exponential number of linearizations to consider. I have to consider all possible orderings. For this execution, I have to consider all possible orderings in which the NQ of 1 is before the DQ of 2, because those are ordered in real time. Otherwise, the other DQ and the other NQ, they can be ordered arbitrarily. So in this case, even though there's only 4 operations, I have to consider 12 possible linearizations. And this number grows exponentially as I increase the number of operations, really limiting implementations to consider very small execution sequences. So it's not just intuitively hard. It's been known since 1997 that this problem is NP hard for arbitrary abstract data types. Our result is to wonder, well, it seems like for some abstract data types, there's a more straightforward reasoning process that might be possible. So maybe this NP completeness result doesn't hold for every abstract data type, but only for in general. And maybe we can point to a class of a finer grained class of abstract data types which have polynomial-time decision procedures. And that's precisely what we're doing in this work. Our main result is that for collection types, their linearizability checking problem is actually polynomial-time. Intuitively, the way we're going to do this is to replace this blind enumeration of possible linearizations with a more monotonic style of reasoning based on deductive inference. And in particular, I'm going to talk about inference over a predicate in a logic that represents the linearization order. So just again, considering the same execution history, we can view this as a partial linearization in some sense, in which the order of operations, if one operation returns before another one is called, there is a linearization constraint between the two. So if we think of that as a partial linearization, now we have to try to go towards a more complete linearization. And we can do that using inference rules for a given abstract data type. So for instance, a queue might have an inference rule which says, well, if I have two elements x and y who are DQ'd in a certain order, then their NQs also have to be linearized in the same order. And so based on this kind of inference rule, we can now additionally linearize this partial linearization one step further to a stronger linearization in which the NQs are also ordered. And in principle, you would just follow this set of steps. In this case, this is already complete linearization, so we're done. This is the only possible linearization adhering to the Q abstract data type for this particular history. The theorem that we show is that checking linearizability is polynomial-time for the collections which admit this kind of inference. So a higher level of our approach here is basically to reduce the logical satisfiability problem to reduce linearizability to a logical satisfiability problem. In particular, we're going to, out of the space of all possible abstract data types, we're going to try to hone in on a set of abstract data types, again, which we call collections, which admit logical characterizations, which can then be reduced to propositional Horn formula. And it's well known that propositional Horn satisfiability is solvable in linear time. So as long as our reductions are all polynomial time, such a reduction would actually give us polynomial time algorithm for linearizability. So the logical characterization that we've worked out has three basic components. We have to encode an axiomatization of linearization order. And I'm just going to write linearization order here as using the less than operator. And so we would have the axioms you'd expect, saying that linearization is transitive, right? It's a total order. So for any two operations, one, either x is linearized before y, or y is linearized before x, or they are the same operation. Besides the axiomization on linearization, we also have to axiomatize the basic inference rules for a given abstract data type. So for the Q, for instance, if we wanted to axiomatize this rule which says that inQs are ordered in the order of their DQs, we could introduce, what we do is introduce a match predicate. Two operations satisfy a match predicate if they're inQing and DQing, or more generally for collection types, adding and removing the same element. And then reasoning about the linearization order between them, right? So for two pairs of matching operations, if their removes are ordered, then their adds are also ordered. Besides these axiomatizations, we also have to encode the execution history itself. We do this in ground formulas, as you'd more or less expect. So any two happens before operations are ordered by linearization orders, for instance, E1 and D2. And the matching operations are encoded in the ground formula as well. So for instance, E1 matches D1, so we have a predicate match E1, D1. The theorem that we give here is that in this logical characterization, linearizability is equivalent to satisfiability of this logical characterization for unambiguous histories. Now I have to go into a caveat here because this isn't true in general, and we have to consider what it is an unambiguous history. So an ambiguous history is one. Now, this is specifically defined in terms of collections, which have operations which do adding and removing of elements. So an ambiguous history is one which adds the same element more than once. So in this example I have here, the element 1 is inQ'd twice, so this is an ambiguous history. An unambiguous history, on the contrary, every element is inQ'd at most once. So I'll get to later about the soundness of this particular assumption, restriction to unambiguous histories. So given a logical characterization, the question is, how can we reduce this to Horn satisfiability? In our logical characterization, in general, the clauses, so even if we did some quantifier instantiation and got rid of quantifiers, in general, the clauses have more than one positive literal, so they're not in Horn form. And in particular, if you think of the totality axiom, this already satisfies this. The totality axiom says either A or B or C, so this is not in Horn form. So the question is, what can we do to get rid of this? We propose a translation here called hornification, which is very specific, and I'll get into how. It's specific into this particular logic, which has only a predicate talking about linearization order. And what we do is we translate this clause into a set of clauses in which each clause has at most one positive literal, and we do this by exploiting the properties of linearization. So for instance, consider the clause B linearized before C. The literal B linearized before C. Now, the negation of this literal is also representable in positive form because the negation of B linearized before C is C linearized before B. Thus, B linearized before C is equivalent to its representation in the first clause here, not C before B. Right? So we consider now all translations, all equivalent clauses to this particular clause in which there are at most one positive literal. In this case, there are 4 of these, including the last one with including the second to last one with 0 positive literals. So the theorem that we have here, and again, this is really exploiting the properties of the one predicate that we have in this logic, is that this translation is equisatisfiable and polynomial-time computable. And this relies on this predicate being the linearization total order. So the question now is, if I have a method to reduce anything that has this kind of logical characterization to Horn satisfiability, to what abstract data types does this apply? And so we identified this class of collection types based on 4 semantic properties that we've come up with that I'm going to go over here. And the first of these properties is parametricity. Parametricity is something you'd expect from concurrent data structures, especially collection types anyways. The idea is that if I take any sequence of operations, for instance, a DQ of 3 from a Q which includes 3 and 5, I can arbitrarily just rename the values. The data structure, the abstract data type does not really care anything about the particular value of 3 or the particular value of 5. I can arbitrarily rename these values. So for instance, if I rename 3 to 7, this is still an admitted sequence according to the abstract data type. That's parametricity. Slightly more subtly and more dependent on the semantics and the semantic characterization that we give in the paper is locality. The idea of locality is that any of the values of a collection which are touched by a given operation or used by a given operation have to be apparent in the label of that operation. So we can see in the DQ of 3, the only value that this operation needs to look at is 3. 5 can be completely ignored, and its label also includes the value 3. Now, I'm giving you an informal description in some sense of this property of to use or to touch a value, but these are precisely defined in our paper based on just purely semantic criteria. On the other hand, an operation like size 2 wouldn't be local. Intuitively, to compute the size, I have to look at both elements in the queue, 3 and 5, and return the value 2. This is not local because neither the value 3 nor the value 5 appear in the signature, in the label of this operation. The third is a little less subtle, which is value invariance, which says that the values returned by operations are just those values which were put in to the collection type. So this is true of, again, DQ operations, but this wouldn't be true of arithmetic operations like sum that return the sum of the elements in the queue, because in general, I've never directly stored into the queue the sum. So the fourth property is the most I would say, far-reaching, and it is called k-reducibility. And it says that, intuitively, it says that I can reason about sequences of valid sequences of abstract data types by reduction to smaller subsequences. And in particular, if I think of a queue, it satisfies a property called 2-reducibility. What 2-reducibility says, if I have any sequence of operations, let's consider this one, to conclude that this sequence is accepted by the ADT, I have to consider all length 2 subsequences. So, sorry, all subsequences with only 2 values. So in particular, if I just look at the values 3 and 5, the values 3 and 7, and the values 5 and 7 in this particular execution, since all of those would be admitted, I can conclude that the bigger sequence is admitted. So this is 2-reducibility. So these are the properties that define what a collection type is for us in this work. And they will have consequences that I'll get into. The most immediate consequence is based on implementations, not the types of abstract data types, that says the restriction to unambiguous histories is sound for implementations which are parametric. So that is to say that if we're looking at implementations who don't inspect the value of particular operations and can just work over arbitrary renamings, then we have the restriction to unambiguous histories as sound. More far-reaching implications, though, combining all of these properties together, are that, and again, the details are in the paper, and I won't have time to go into them, are that collections have what's called bounded violations. So if I take an arbitrary long trace of a collection abstract data type, I can always point to one of a small number of small violations, for instance, of the queue above, such that larger non-admitted history embeds one of those small violations. So in particular, if I think of a queue, what are the minimal violations? The minimal violations are, there's a pair of matching NQ and DQ, and the DQ is linearized before the NQ. This is a violation. Or the slightly more complicated one that we discussed before already, which is if I see 2 NQs in one order and their corresponding DQs are in another order, that's a violation. So the properties of collection types, especially 2-reducibility, for instance, gives us that any history has to embed one of these minimal violations, and these minimal violations are bounded in number based on the properties of being a collection. So this is rather strong, and it leads us pretty much directly to a logical representation for collections, for any given collection, which is basically just a logical characterization based on the conjunction of negations of encodings of these bounded violations. So for instance, the first one that says a DQ is linearized before it's matching NQ, this would be, x1 matches x2, and x2 is before x1. So we just want to negate that to make sure this pattern doesn't happen. So this gives a logical representation. And the theorem, again, combining all this together, is that collections have sound logical specifications. The corollary to this is linearizability is polynomial-time computable for collection data types by reduction to Horn satisfiability. So just to emphasize a little bit that this work isn't only of theoretical interest of considering asymptotic complexities. In a previous work in POPL'18 2015, we've actually implemented these basic algorithms, and we've compared it with the naive enumeration. We've compared SAT-based encoding and our further optimization to Horn SAT-based encoding. Now, to test out basically the performance, I basically considered runs over 10 histories with 10,000 steps each, and considered various timeouts from 5 seconds, 25 seconds, all the way up to 100 seconds, and see how many steps, see how many events each algorithm can process in that timeout. So as we can imagine, the enumerate doesn't get very far. In this case, it ends up averaging just 32 steps in 100 seconds. Well, the stat encoding can outperform that quite a bit, maybe doing double, based on probably just avoiding redundant enumeration. The horn set goes much further, in an order of magnitude better. I've also put on this graph an optimization, which I didn't discuss, which is in the PLDI paper, and you can look at that, which involves reducing, pruning from the history operations that are obsolete in the current context of where we are in the trace. So this is somehow some indication that this algorithm actually has some practicality to it, but it was a little upsetting because in the context of coming up with runtime monitors, I wanted to see something that could scale linearly in time. So what we did was, it turns out that at least our implementation of the algorithm, we didn't just use a horn solver. We had a custom inference algorithm that we implemented ourselves. In our implementation, that was a polynomial-time algorithm because we always have to consider every pair of values that are currently in the collection. So normalizing these numbers over the collection size squared shows that, right, for a fixed size collection, if I said I'm only looking at queues now of up to size 10, we can actually monitor in linear time with our algorithm, at least empirically. I don't have any asymptotic proof of that. So these are the numbers normalized to the collection size squared. So just to cover quickly related work to finish up. So the initial enumerative-based linearizability checking algorithm was given by Wing and Gong in the 90s, later shown to be hard by Gibbons and Korok. Since then, in the decades following, we've seen some asymptotically equivalent optimizations. Recent work by my colleagues and I have shown tractable yet generally unsound approximations to linearizability checking. We've also, the logical characterization that we showed today is based on, as I said, our PLDI 2015 paper. And we've also come up with a way to automatically infer the logical specifications required for that characterization from doing basically sampling of small executions. And this appeared in POPL in 2016. Thank you for listening.
Questions? Also, please feel free to use the online system to ask questions.
Very nice talk. Very nice talk. I'm curious about the relation between your work and the work on aspect-oriented linearizability proofs by Hensberger, Buffet, and Sesgin. So they also have axioms for data types. And what you're doing is checking some axioms on dynamically generated histories.
Saying checking axiom?
Checking axioms on orders in dynamically generated histories. Mm-hmm. Are those similar axioms? Are those the same axioms? Could you elaborate on that?
So I haven't. I mean, so the general the work that they do is specific to queues and so on. But I haven't checked whether our axioms are in direct correspondence with theirs. I mean, the main I would say technical thing that our work is giving is a generalization of that to other types. So you can plug in a logical characterization for an arbitrary abstract data type. If you show that this logical characterization is now complete for that data type, now we have a polynomial-time algorithm for checking it. So it's more about the mechanization of, in particular. So I didn't go into depth about the particular axioms that we're using for queues, for instance, but they probably are quite similar.
All right, thanks.
Yeah.
One last question.
Is there a dichotomy theorem that shows that this is the best possible class that you can get? That if you relax any of the assumptions, you get NP completeness?
No, but I mean there is. So Gibbons and Korok did show, for instance, that their result about NP hardness is true for registers, which we call a collection type. So in fact, but what their result relies on is analyzing all possible histories. So our recognition that you can actually soundly consider only unambiguous histories is actually really important. So if, in general, the register would be an NP-complete thing. So that's a relaxation. If you relax that, you would have still hardness. Yeah.
All right, let's thank our speaker again.